We're looking at types of acceleration now. So we understood acceleration. Now we are looking at types of acceleration. So the basic idea is how much velocity has changed in the given time. Okay. So average acceleration is to do with, we are not looking at how complex the velocity is changing and how rapidly or what is the rate at which the velocity is changing every second. No, we're not doing that. We're just going to average it out. So graphically, acceleration is the slope of a straight line connecting the two corresponding points between this in a VT graph. So let me show what it means. Say we have a velocity time graph. And we have some graph like this. It doesn't matter. Or it can go this way also, up and then down. Say I want to figure out the average velocity between, I think I took it as V1 and V2. V2, V1, T1, T2. So this is V1, T1. And this is V2, T2. Now the average velocity is just taking this and finding the slope. So this is velocity time graph. So this is in meter per second, for example. And this says in second. And so this, the slope of this, that is the slope of this line, connecting line, will give you guys acceleration. That's it, right? So let me make this as dotted line as well. Yeah. So acceleration is the slope of a straight line connecting the points corresponding to V2 T2 and V1 T1 in VT graph. Right? So I do have a video apparently. So this basically. So this is a velocity time graph. And this will give us the average acceleration between these 2 points. Now, the mathematical form of this would be what? Suppose an object that has been modeled as a particle moving along the x-axis has an initial velocity of vxi, and at a time of ti, the final velocity is vxf at time tf. Then the average acceleration ax of the particle is defined as the change in velocity divided by change in time during which the change occurs. So we have average acceleration math. So average acceleration along the x-axis is given by change of velocity along the x-axis divided by change in time. And change, since we already have values over here, let's substitute that. So Tf minus Ti. That's it. Right? So that's your mathematical representation. Then the other acceleration is your instantaneous acceleration. So instantaneous is to do with what? Remember, what is it? So it's like having a magnified glass to see exactly how force are making things go faster or slower at any given moment. That is a very small interval of time. That's the idea of instantaneous. We have seen this quite some time. And the entire chapter is dedicated in mathematics, that is your limits and derivatives. So definition is instantaneous acceleration is equal to the derivative of velocity with respect to time. So mathematically, let me go here. So now I'm teaching you guys and we are learning instantaneous acceleration. So mathematically, instantaneous acceleration is defined as, say along the x-axis, it will be derivative of velocity of x with respect to time. Of course, there are many ways of writing this. So this is how we define it. Another way to define it is limit change in velocity with respect to time as time change in time tends to 0. That's one of the another way of defining your acceleration. Instantaneous acceleration. Okay, and graphically it will look like this. So till now it has been average acceleration. Now we are approaching and we have almost reached instantaneous acceleration. So basically the tangent at a given point gives you instantaneous acceleration when it comes to a velocity time graph. Let me put it on the, so this is still instantaneous acceleration in graph. Which graph? Velocity time graph. So we have a VT graph. So this is V and this is T. Velocity time graph. So if I have some anything, anything is happening. So if I want the velocity, instantaneous acceleration, sorry, not velocity, instantaneous acceleration at say some point T. All I have to do is if you have a graph, my suggestion is just take a scale, draw a tangent over there and measure the angle and find tan theta and you're done. So that's the whole funda, right? So you can approach it in this way, thinking about in books, this is what we see. They explain it this way, basically. So we have 2 points, A and B, for example, and the slope is giving us your, same color. Let me take a red. The slope of this line, red line, this slope is your acceleration. Now, this is your change in time. And if I project this onto the y-axis, again the same color, my bad. And let me use a lighter. So if I project it onto your y-axis, this will give us change in velocity. So when this approaches, when delta t approaches 0, for delta t tending towards 0, the slope will be tangent at A provided B is moving. At A or B, actually depends which side you guys are moving. So depending on the direction that is closing up. Where we are moving. Oh, you guys are not able to see that. I'm writing it a bit on the right as well. Where we move. Okay, so that will give us the slope. Right? Instantaneous slope. That is your tangent and that is your acceleration, instantaneous acceleration. Okay, yes. So not a difficult concept if you again know limits and derivatives. If not, you're just here, seeing something which will not make sense. So this is, if not, it's just 9th grade syllabus. Without limits and derivatives, it's just 9th grade syllabus. Corresponding to this, I have, and then mathematics, and this is the write up. And then we have instantaneous acceleration.